Thus far, in our discussion of quantum mechanics, we've presumed that we can make a measurement. This measurement forces quantum mechanical systems into eigenstates of the quantity being measured through some process we've called, for convenience, the collapse of the wave function. There is, however, a major problem. We do not know what a measurement is in quantum mechanics. Worse, we cannot construct a model of it in the quantum mechanics we've constructed with linear operators acting on states. And we can prove that we can't do this. That is, we can prove that the machine or process that's to perform this collapse cannot be described by quantum mechanics, at least not the quantum mechanics as we've written it or defined it so far. Now we're going to look at this difficulty, what we call the measurement problem in quantum mechanics. Suppose we have a measurement apparatus that's going to act on a quantum mechanical state to give a measured value. Now, we want our quantum mechanics to be a complete theory, so this measurement apparatus itself has to be a machine that can also be described by quantum mechanics. As a result, it can be described by a quantum mechanical operator, which we call M for measurement. This operator takes the physical state of the system being measured as its input, and as a result collapses that state into the measured value as its output state. Since this operator M, representing our machine, is representing a quantum mechanical system, by presumption in quantum mechanics, this operator M is linear. Because of this linearity, we can write down some properties of how this measuring system behaves. So let's see what are the consequences of that linearity.
So let's look at our proof of the measurement problem then. Suppose that the system starts out in one of the eigenstates of the quantity, such as electron spin, that's being measured by the apparatus. Hence, for the initial eigenstate being spin up, for example, the result of the measurement process will be the state spin up. That is, the measurement apparatus described by this quantum mechanical operator here, because the measurement apparatus is presumably quantum mechanical, operating on the spin up, should give us spin up. That's the result we want from our measurement apparatus when it's measuring the state that is spin up. When measured in an eigenstate, the system therefore should stay in that eigenstate when we perform the measurement. Similarly, for the other possible initial eigenstate, the measurement apparatus acting on spin down in this case should give us spin down. So far, this agrees with our observation. But suppose instead that the system starts in a linear superposition state. Then, on operating on that state, because of the linearity of this operator, because the measurement system is presumably a quantum mechanical system, we have that the action of the measurement system on this linear superposition gives us the linear superposition of the measuring system acting separately on the components. And that means that the measurement system acting on this superposition gives us the superposition of the states. Note that this resulting state then is a linear superposition also.
The measurement operation has not been able to collapse the resulting state into an eigenstate, in disagreement with our understanding of measurement. Therefore, there's no way of describing measurement using the quantum mechanics we've constructed. There's no proposed solution to this difficulty that does not appear either absurd or that invokes something outside quantum mechanics for which we have no explanation. Also, there is no experiment that we know of that can discriminate between the different proposals, and therefore all of them remain in the realm of metaphysical, philosophical speculation. Next, we'll briefly mention some of the contenders.